Good morning. In this talk, I'm going to discuss interpretation of magnetic field data that's due predominantly to remanent magnetization. And I'll present some case studies from the Coompana area of South Australia. In the talk, I'll go through the resultant magnetization and its inversion. We'll look at Helbig's magnetic moment analysis, and then we'll look at the case study from Coompana. We'll look at a simple anomaly. We'll look at selecting a drill target. We'll look at dealing with a complex magnetization, and then draw some conclusions. The external magnetic field of a source is a function of the vector resultant of its induced and remanent magnetizations. The induced magnetization is generally in the direction of the geomagnetic field and proportional to the magnetic susceptibility. The remanent magnetization can be in any other direction. The traditional measure of the importance of remanents in magnetic field interpretation is the Königsberger ratio, which is the ratio of the intensity of the remanent magnetization to the intensity of the induced magnetization. But this is a scalar factor, and it's not sufficient to explain the vector triangle that we need to work with. So I'll suggest that we also add in a term of the angular departure between the geomagnetic field at the site, which we know, and the resultant magnetization direction, which is the direction we recover from the magnetic field interpretation. So how do we invert for magnetization if we have a magnetic anomaly that we want to explain as due, for instance, to a cube of induced magnetization, we'll consider in the first case? We can describe that cube of magnetization with 5 parameters. We have 4 spatial parameters: the x, y, z coordinates of some reference point, the side length A, and the magnetic parameter, which is the susceptibility K. We need a forward modeling code to compute the field of that cube at our measurement positions. And then we need a second piece of code which will call that forward modeling code repeatedly and try to optimize the set of parameters. That optimization code is not a magnetic code. It's not even a geophysical code. It's a general optimization procedure. If we go to working with remanent magnetization, we can no longer recover an estimate of the susceptibility, because the susceptibility is no longer the only explanation of the field. We also need to consider the remanent magnetization. So we take away susceptibility from our set of parameters, and we add in 3 parameters that describe the resultant magnetization: the intensity, the declination, and inclination. The declination and inclination can be a little bit difficult to work with because they're angular terms, but not particularly difficult. If we have problems dealing with those, we can alternatively look at the magnetization in terms of 3 vector components: mx, my, mz. Each and the amplitude of each of those is just like the k term that we had in our first inversion. The forward modeling to address remanent magnetization as well as induced magnetization, there is very little addition of complexity to the code that we have for an induced magnetization. There's only a very slight increase in complexity in the forward modeling code. In the inversion code, we've gone from 5 parameters to 7 parameters. That's no concern. We'll generally be running inversions with hundreds or thousands of parameters. We have a little bit of complexity of dealing with the angles, but not very much. So if we can run an inversion with induced magnetization, there is no big problem to running an inversion with resultant magnetization. It is not a big jump. It's a very small change to go from working with inversion of induced magnetization to inversion of resultant magnetization. But we need to consider how we interpret the data. The problems of interpreting inversion data from potential fields are almost completely dealing with the non-uniqueness that arises. So what non-uniqueness, additional non-uniqueness from the induced case, do we introduce by moving from a case where we say that we know the magnetization direction to the case where we don't know the magnetization direction? And the place to start answering that question is with Helbig's analysis. Helbig's analysis tells us, is an analytic proof, that if we have a dipole of a known position And if we map the three components of the field, Bx, By, Bz, in a plane above that dipole, that we can recover the strength and direction of the dipole from the magnetic field interpretation. That's an analytic proof. The X, Y, Z components we can derive from TMI data by an FFT transform. The FFT transform depends only on the geometric direction of the field. It doesn't depend on the source magnetization. So in the case that we have a dipole, we have an analytic proof that we can recover its magnetization direction from the magnetic field. But the moment we step away from that dipole, we're going to lose that analytic proof. But we should expect that if we have sources which are at least dipole-like, that we will only gradually lose the ability to recover magnetization as we move away from to sources that are less and less like a dipole. Let's move into the real world. This is the Australian Remanent Anomalies database. This is being produced by CSIRO in conjunction with Geoscience Australia to assist geoscientists working with magnetic field data. The minimum condition for entry into this database is simply to tag an anomaly as being recognized as possibly due in some part to remnant magnetization. At present, we have about 300 entries in the database. Each of these entries currently has a full image of the anomaly, and each of those solutions has one or more models to explain it, together with estimates of magnetization direction. In this talk, we're going to look at some case studies from the Coompana area in South Australia, which is in this red box. This is a part of a TMI image over the Coompana area from a survey recently acquired for the Geological Survey of South Australia as part of their PACE Copper initiative. And I'd like to acknowledge my co-workers who've worked on this magnetic field data with me, Ryan Dutch, Gary Reid, Tom Wise, and Tim Keeping. We're going to look in this talk, we'll look at the simple anomaly A up in the north. We'll look at a smaller anomaly B over a shallow magnetization to the south, for which we want to derive a drill target. And we'll look at the complex distribution of magnetization in area C. This is anomaly A to the north. It's a simple anomaly. We need to interpret it. We need to make a separation from the background field, so we need to interpretively define a regional field. And then we'll ask the inversion model to explain the anomaly which, added to the regional field, gives us an approximation, and we can see in this case a good approximation to the input data. This is a simple anomaly. There's very little evidence of structure in that anomaly. We should consider that we can only really justify having a simple model. This is the top plan of our best, our preferred model, and we think this has an appropriate degree of complexity to recover all of the information in the anomaly, but not to add too much complexity that we cannot justify. It would be really nice to have a metric for these anomalies that describe how much complexity there is in the anomaly, and that would allow us to then give an appropriate degree of complexity to our model. Unfortunately, I don't have that metric, but we'll see a way of compensating for it. So this is the model. It's preferred also in part because we've put a planar top on the top of the model, because we expect the magnetization to be terminated at a basement unconformity, which is subhorizontal. The depth of the top of the body, the depth of the top of the body beneath the sensor is about 1,200 meters. The maximum horizontal extent of the body is about 3.5 times that, and the maximum extent, which would probably be possibly between this point and that point, the maximum extent of the body is almost 6 times the closest approximation of our measurements. And I'd suggest that this estimate, this statistic of maximum extent to closest measurement of our model, we can use as a proxy for this measure of simplicity or complexity that we would have liked to have had from the anomaly itself. This body I would put into a classification of being moderately compact. If it had a value of 2 or 3, it would be highly compact. We would get no possibility of mapping out any internal structure. With a value of 6, we have very little indication of complexity of the anomaly. This simple, relatively simple geometry and homogeneous magnetization explains the anomaly. We are not justified in having any more complex model. Unless we have some additional information, we have no justification to build a more complex model. Explaining the magnetization, the anomaly with a homogeneous magnetization, we have no justification in having an inhomogeneous magnetization. There is no justification for that. So we should not build any models much more complicated than this. What about this model, this simple model? Is this a reasonable representation of the magnetization in the Earth? Is this an image, a potential image of the magnetization in the Earth? It isn't. It's highly unlikely that the magnetization in the Earth is going to have this simple geometric shape. It's highly unlikely that it's going to be homogeneous. So we can't accept a more complex model. What can we accept from this simple model? Here I've run additional inversions using different geometries and using different forward modeling codes. The most consistent factor of these, and each of these models explains the data quite well. In fact, almost equivalently. There is a slight difference in the post-inversion misfit statistic for each of these models, but not in a way that you could use it to discriminate and choose one model beyond the others. So each of these is a potential explanation of the model, of the anomaly. The most consistent spatial parameter for these three bodies is the center. The center of these bodies clusters very closely. So there's a cluster of centers for these three bodies, which is consistent. That's the most consistent spatial parameter that we get from the model. You can see they have different shapes, but each explains the anomaly. So shape is obviously not a reliable factor from the inversion. Each of them has a different top, so depth to the top of the body is not reliable. The center position is reliable. There's a second reliable factor in this image, which is the direction of magnetization. These models have a range of magnetization direction of about 3 degrees, which is no range. I mean, they're all the same magnetization direction. So the direction of magnetization is reliable, the center of the body is reliable, and not much else. Those particular bodies have a range in volume of a factor of about 6, and a range in magnetization intensity of about 6. And we could find other bodies that would extend that range. But if we multiply the magnetization intensity by the volume, those points lie on a common value, which is a measure of the total magnetization of the body. That is also consistent. I don't have any voxel models for this anomaly, but if I had voxel models, I would expect that if you took the volume and magnetization intensity for those models, they would also fall somewhere on that line with the same product of volume and magnetization intensity. So that's the third factor which is reliable. So we have total magnetization, we have its center, and we have its direction. Reliable. Unreliable, we have volume, intensity of magnetization, shape, depth to top, and we cannot comment on the homogeneity or inhomogeneity of the magnetization. So if you go back to this direction and ask what that magnetization direction is, that magnetization direction is our best estimate of the average magnetization causing the anomaly. That magnetization may be homogeneous, in which case it has a value close to that. It may be highly inhomogeneous, but would still have to have the same average value. So let's look at the drill target that we have to the south. This anomaly is of similar complexity to the first one we looked at. It's much shallower source, but it's a similar degree of complexity. We can see a little bit of structure. We can see from this elongation of the trough that we expect an elongation of the source in the north-south direction. And here I've got two inversion models of an elliptic section sheet and a polygonal section sheet. You can see again the difference in depth at the top. The center points, again, are very similar. The maximum extent to closest approach for these bodies actually is quite similar to what we had before at 5.5. So again, I would call this a moderately compact source. We're not going to be able to look at internal structure in it. Last week, we got the drilling results for this which I've shown. This is an approximate position of the borehole. We don't yet have the navigation down the hole plotted up, so I've just put the total depth in a straight line. The body ended in this model still, but we do need to pull this up a bit because the hole isn't straight. The intersection here is basement into a dolerite, and we have some core that we'll be measuring remnant magnetization on. Our polygonal model was 8% too shallow. Our elliptic sheet is 5% too deep. Both of those are really good results. To get within 10% is I think, quite acceptable. If we're really greedy, we'll take the mean of the two models. The sensitivities that we have. Here I've offset the direction of magnetization and looked at the post-inversion misfit of a model which has an offset magnetization direction. The best models that we have are in the large symbols, and they are the best misfit. That's how they're defined. And they're very similar for both models. When we come to depth, again, I've done the same thing. I've offset, in this case, the depth to be deeper and shallower. You can see that the sensitivity to the model, in terms of increasing data misfit, is much less for depth than it is for the direction. If we try to equate it, a 15-degree difference in magnetization direction equates to about a 30 to 40% variation in depth to that source. This is for this particular anomaly. So if we're happy in getting depth out of magnetic field data, we should certainly be happy in getting magnetization direction for compact sources. Let's quickly look at a complex magnetization. If you see a total field image like this, I don't believe that you should be able to expect to drop that into an inversion package and get a sensible answer. We need a strategy, and the strategy that I would suggest is to try and break it down into smaller parts. We have a positive lobe to the north, a negative lobe to the south, which seem to be part of an outer incomplete ring of magnetization. We have two steps inside, a step here and here. So we have an internal negative, which is due to a strong reverse remnant magnetization, an outer, more diffuse, or thinner, or deeper zone of reverse magnetization, and then these two lobes that we need to explain. The first conceptual model that we had to try and explain that was that they're due to polarization by a sub-horizontal magnetization. And we can produce those two lobes, but we can't produce the sharpness of the gradients or the sharpness of change in gradient. We found it much easier, much more successful, to explain the anomaly with a normal and reverse magnetized zone. We dropped those outer zones into the model, digitized to the outline of the anomaly. We put two sheets in here. This is the model after. This is looking down in plan view on the model after inversion. We had a small body in here to explain. You can see that there's a slight increase in magnetization, and I'll show you why we wanted to do that later. So we have two sheets, an internal sheet with high magnetization and an external sheet with lower magnetization surrounded by these rings. It matches the anomaly extremely well. And these anomalies you can't accuse of being simple. You can see the sharp angular changes in trend of the anomaly. I mean, it is a complex anomaly. We've really matched all the detail of that anomaly very well. The model is an inversion to match a huge area. It's not going to match the data reliably in any one place. And we need to do that to get a depth estimate. So here's this is a total gradient image to try and highlight distribution of magnetization, and we're going to focus on this central body, which is what we tried to explain with the body in green. We have a new body here with a dedicated inversion just of that area. Estimation of depth from this anomaly is just not as well suited to depth estimation as the first one that we started with. So when we got the depth results back from this drilling, I was concerned. And the only way to explain this is to say we got lucky. You know, I think this is a very lucky result. I would have taken a 20 or 25% error on this one, but we're within 7% of the depth below sensor. So we drilled down, hit the gabbro at 374 meters, and we've got another 300 meters of gabbro to measure remnants properties on. The magnetization directions, the southern ring segment and the inner zone, very similar magnetization directions. The outer ring zone, which is more diffuse and has a hole in the middle, is less reliable. This small body that explained the central anomaly in the main, not inversion, is completely unreliable. This is the normal magnetization of that northern ring segment. This is the direction of that central body in its own dedicated inversion, and it brings it in very well into agreement with these magnetization directions. So in conclusion, we can recover reliable estimates of resultant magnetization from inversion of anomalies due to compact magnetizations, that is, magnetizations close to being a dipole. Magnetization direction for these bodies is more reliably recovered than our estimates of shape, volume, or depth. And with appropriate strategies, we can recover multiple magnetization directions from complex anomalies due to immediately adjacent sources. And finally, as more as a recommendation than a conclusion, these anomalies can only be explained with resultant magnetization, with non-induced magnetization. Most remnant magnetization has more subtle expression in the magnetic field, and in many cases, it's addressed with an inversion which only allows for induced magnetization. If you think you only have induced magnetization, by all means run an induced magnetization inversion, but subsequently try and run an inversion with a free magnetization direction. At the very least, it will confirm your idea in the first place that it was induced. If not, if it's different, then it may give you some additional information. I'd like to thank the Geological Survey of South Australia for allowing me to be involved in this Coompana project. The data is available from their website and from the Geoscience Australia website. We have new gravity data over this area, and at the AGC conference in Sydney in February, we'll be presenting combined interpretation of gravity and magnetics. And thank you for your attention.